before we begin? There are a few more homework problems for chapter 2, and I'll probably have them due early next week. I don't know if it's Monday or Wednesday. I've got to look and see how many there are. But start where you're ready to do all those remaining homework problems. I just haven't posted the due date on the website yet. So take a look at those, and hopefully I can get it up this afternoon. Okay, so we're going to talk about, well, we've been talking about analytic techniques to get exact solutions for the energy eigenstates or stationary states, or solutions to the time-independent Schrodinger equation, right? We would call them the stationary states once we add in the time dependence, or separable solutions. We have a lot of different names for those. But what I want to do is just spend a minute talking about how to gain some intuition about what solutions would look like to some other potential for which we just only know kind of the crude shape of it and how to qualitatively sketch them. And we already have a lot of the tools, but I just wanted to put them together in one place. So the first thing I want to point out is that when we look at the time-dependent Schrodinger equation, or that is the Schrodinger equation, at any time, the wave function shape at that time, the waveform it has at that time, could be just about any complex function you can make up, right? As long as it's normalizable, if we're talking about a single particle solution. But the time-independent Schrodinger equation, if we try to find the solutions corresponding to a well-defined energy E, are really highly constrained. You can't have a solution to the time-independent Schrodinger equation corresponding to an energy E be just about anything. And as we've been finding out, we get these infinite collections, but they're very definite shapes. And we want to kind of figure out for other cases, and in the worksheet that we're going to work on there, and maybe we'll do the first one together as we're going through these sketching guidelines, we can figure out qualitatively what, the n equals 4 state looks like if n equals 1 is the ground state. So, Griffiths produces, this is from the harmonic oscillator, exact solutions that look like this, but we're going to learn to qualitatively draw the n equal, ground state, first excited state, second excited state, and so on, to get, the qualitative features right. So the rules, we'll just go through them one at a time, and maybe I'll draw, I'm not going to switch the camera, but you can enlarge this if you want, Alvis. I'll draw the first example from the worksheet that I've passed out, which is the one from today, where we've got a potential that doesn't look like anything special. If I plot the potential as a function of x, it looks like it keeps going up in a linear fashion as you go to more and more negative x's. And then, I didn't think too hard about drawing this. Then suddenly it jumps up to a higher value, and it keeps that higher value from then on. And we want to draw a particular state. And at least in this worksheet, since we've switched our mind between the infinite square well and the harmonic oscillator about what the ground state is, n equals 1 or n equals 0, I'm just going to assume for the purposes of this worksheet that n equals 1 is ground state. And we want to find, let's assume that there is a bound state. I know it's a bound state because the energy I'm going to draw is asymptotically below the potential energy on both sides. And so if this is an allowed bound state for this particular potential, then well, it will be a bound state. And what I mean by E4 is that it corresponds to n equals 4, where n equals 1 is ground. Otherwise, we wouldn't really know what n equals 4 means. Okay, now this first one we've talked about before, and actually many of these we've talked about before, and it doesn't apply to this potential, but sometimes we'll have potentials that are nice and symmetric. And we've already stated, you can imagine, just because in solving If you start at a point in the middle and you solve the differential equation to the right, maybe numerically in MATLAB, and then solve it to the left, something symmetric is going to happen as you head in those directions. And so if we have a symmetric potential, we expect the, I'm getting ahead of myself. This is about the reality of the solution. If we're talking about a bound state, we can assume the solution is real. We can always generate complex solutions, but whenever we've been drawing them, we've been drawing real functions. And that's just because the time-independent Schrodinger equation doesn't have any i's in it. There's no imaginary part. So if you don't start out with an imaginary starting point, it'll never go imaginary. It just changes in the real direction. So, if I give you a solution to the time-independent Schrodinger equation, say the ground state for the harmonic oscillator, it's true that I times that is also a solution, and that would not be a real solution. So there's no fundamental rule that the solutions have to be real, but we like drawing real functions. And we can always assume that they're real, and all the other solutions that we might find are just complex multiples of those solutions. So we're going to always choose the solutions to be real, just like the functions that Griffiths is drawing there. This is what I was about to say. If you have a left-right symmetric potential, or a potential that is symmetric with respect to some other point on the axis, then the solutions are either even or odd with respect to the center of symmetry. And usually we place that center of symmetry at x equals 0. So they're what we mean by even and odd solutions. So as you go up in energy, the ground state is always going to be even, then the first excited odd, and so on, alternating back and forth like that. To start sketching, now, of course, that doesn't apply to this potential that I'm looking at here on the board, the first one on the worksheet, because it doesn't have any special symmetry. So to sketch qualitatively a solution, the first thing that's important to do is to mark out the classically allowed regions on the axis and the classically forbidden regions on the axis. And in this case, that happens, classically allowed is where the energy is greater than the potential energy. So in this, if I drew a little region here, this region right here is what we would call the classically allowed region. If the energy is less of the particle is less than the potential energy, that's what I'm calling classically forbidden. Okay, and of course, it's going to behave differently in those regions. In the classically allowed region, it's going to oscillate generally. In the classically forbidden region, it's going to decay away towards 0, or at least have some sort of decaying behavior. That's what this says. So the psi oscillates in the classically allowed region. So here we have oscillatory behavior. And then in the classically forbidden region, it's either exponential growth. Well, it's not exactly exponential, but growth or decay kinds of functions. So this would be decay, since it's going off to infinity, and decay towards minus infinity. All right, and you can see that just by looking at this differential equation. If v were constant, then this whole thing would be a constant, right? If we're in a region where v is constant, and of course e is constant, then E minus V is going to be constant, and this would be, say, in the classically allowed region, would be the harmonic oscillator differential equation. And if V were constant over here, this would be the exponential differential equation, one that has e to the something x or e to the minus something x as a solution, right? If V is not constant, that means the solution is not exactly sines and cosines, or the solution to this one is not exactly exponential growth and decay. But qualitatively, it's the same thing. So it's going to look kind of the same. It's just not exactly sines and cosines. Now, how does E minus V, the magnitude of the difference between the energy of the state I'm drawing and the potential, affect the behavior of the oscillation if you're in the classically allowed region? Well, as we know, when the difference between the energy and the potential energy is larger, it oscillates more quickly, right? If you think about the free, well, you can just look at the differential equation there. So we already know if you have a constant difference between those, it oscillates, and that k is related to E in, in the same sense of like K is equal to root 2m E minus V over H bar in the classically allowed region. So if V is constant, that means the oscillation frequency is determined by this difference. Bigger that difference, the higher the oscillation frequency in the classically allowed region. Similarly, in the classically forbidden region, it decays away more quickly the larger the difference between E and V in that region. Okay, just if we're talking about bound states, the wave function has to decay away to 0, of course, as you go to plus or minus infinity if you're in the classically forbidden region, and you should be if we're talking about a bound state there. And the examples I'm going to draw on here are of bound states. We also have to make sure we preserve the continuity of psi and, if appropriate, the continuity of the derivative of psi with respect to x. For bound states, the number of zeros is always, it depends on your convention for labeling, but if we call n equals 1 the ground state, then there should be n minus 1 zeros to that function that we're drawing. Now, this is something that's worth dwelling on for a second. It doesn't tell us about actually the bumps directly in the function. If you look at the harmonic oscillator, you might say, hey, well, look, the ground always has one bump. The first excited always has two bumps to it, right? Two hills or hills and valleys, and so on. But that's not necessarily true, although the zeros is true. One case where we can illustrate that shows that that's not true is that well pair kind of potential, where we're talking about, and let's see, no. Oh, that's not going to work. There we go. Okay, so what I've made is some ground states inside a double well. Okay, so I've got a well with a barrier in it. And these states are very close together at the bottom, but my well is symmetric about x equals 0. So I'm expecting a ground state that's even and a first excited state that's odd. Now, in this case, so if I go to the ground state, if I try to move it just to the right spot here, there's the ground state. And you might complain and say, well, look, it's the ground state, but it actually has 3 bumps in it, right? Here's some sort of minimum, and here's a maximum and a minimum and a minimum. So it doesn't look like what I was expecting for a ground state. I'm expecting for a ground state to just have 1 bump. But notice that if we call this the 0 location, this is where it's being graphed across. It's only got 0 zeros, right? It starts decaying away and it asymptotically approaches 0 over there. But there's 0 zeros in that case for the ground state. And similarly, as if I go up to the first excited state, if I can just barely move this up, then we start to have 1 0. Second excited state, I keep missing it. There it is. It's got 2 zeros, even though it looks like it has a lot of bumps to it. So in general, you can't count on those bumps, the peaks and the valleys, but you can count on the zeros, right? No zeros for the ground state and increasing as you go on. Okay, so that means in this case that I'm graphing on the board, we're told that this is the n equals 4 state. So let's see if we can fill in some of the information here about this state. In my video. How many zeros am I expecting here if n equals 1 is the ground state? 3 zeros, okay? And those zeros are all going to occur in the classically allowed region, because in the classically forbidden region, it's just decaying away towards 0 asymptotically. It's not going to cross the axis and go there. If it crosses the axis, it would have to oscillate again to come back around. So I'm expecting 3 zeros in this classically allowed region. If you're following Griffiths, whatever the energy of the particle is, there's no sense, or this, this isn't necessarily a logical thing to do, but it's kind of nice to draw it this way. You've noticed that Griffiths, when he's drawing the harmonic oscillator states and he has the various energies here, he happens to choose whatever line represents the energy and takes that to be the zero of the wave function. And then, does his wave functions relative to that line, right? That doesn't necessarily make any sense, but it's a perfectly useful thing to do. So we're going to draw our wave function sort of bouncing around this line as if this is the psi equals 0 line. So what I'm expecting is this thing to have 3 zeros in this region, and I might just, for the sake of argument, put them equally spaced within the classically allowed region. What do you say about my spacing there? That's actually inconsistent with one of the previous rules, that in this classically allowed region, I'm expecting 3 zeros and I'm going to place them on my axis, which is just the energy line there. And I've equally spaced those zeros there. How should I amend that to agree with the notion that the higher the energy is above the potential energy, the shorter the wavelength? Right? We usually think of short wavelengths as being high energy kinds of things, right?
I would say to keep the points evenly spaced in terms of each other, but compress them more.
Yeah. So, what you mean? Compress them toward the center?
Yes.
Or, well, so let's imagine that if I try to draw something here without worrying about the zeros, I'm going to try to draw a function whose wavelength gets smaller as I go to the right, right? Because the energy relative to the potential energy is getting bigger, and that means it's going to oscillate more rapidly, right? So let's draw a function that sort of oscillates more rapidly as it goes to the right. What's happening to the locations of the zeros?
Oh, they're
getting closer and closer and closer together the faster it oscillates, right? So that means I shouldn't have these equally spaced here. The first one might be here, but this, they should be getting scrunched together there. Again, I can't say exactly how it should be, but I'm trying to match things, make as many tweaks as I can to make it kind of agree. Okay, and let's see. I'm supposed to have decay over in this region, so it should be decaying towards 0, right? It's not really technically exponential growth and decay. And then, well, let's see, it's got to oscillate in this region, so I'm going to try to hit those zeros with some oscillation, right? Goes here, comes up, and it's got to be ready to decay back towards my, nominal axis line over there in the classically forbidden region. So that's what I've got so far. We're not quite done with the rules yet, but that's what I'm trying to follow all the rules that I have so far. These can't be equally spaced because the wavelength is getting smaller as the difference between the energy and the potential energy gets bigger. All right, let's go back to the rules. Finally, 9 is one that I'm going to explain intuitively to you, and there's a more analytic explanation of it on the backside, which I'm not going to go through, but you're free to read through. You don't really need to know it for the purposes of testing in this class. The amplitude of an oscillatory piece increases when the wavelength increases. Okay, and that means that what I've drawn there wasn't very careful. Here I drew something as if the amplitude was constant, right? What this rule is saying is that as the wavelength gets bigger, that's on the left side of my figure here, the amplitude should be getting bigger. And we'll try to resketch that a little bit more accurately in just a second, but let's look at an intuitive reason for that. So I'm just going to take a very simple case where I have a potential that is a lower constant here, and then it jumps up to a higher constant, but we're talking about a state that is where the energy is above the potential energy in both regions. And maybe it changes as you go off to plus or minus infinity, but that's what it looks like in this region. Okay, so let's try to, in both these cases, this is all of this is classically allowed, so we're expecting oscillatory behavior, and in fact, since V of x is constant, we're expecting pure sinusoidal behavior in both these regions. So let me just draw a little sinusoid there. And let me draw a continuation of the sinusoid. And immediately I can see that's not going to work because the wavelength should be getting larger as I go to the right. Wavelength should be getting larger because smaller wavelengths correspond to higher energies, energy above the potential energy. So that's not going to work. So let me just redraw that with
Wait a minute. Is anything on the screen?
Oh, I'm sorry. Did I forget to reshare? Thank you, Alvis. Always speak up when I forget to reshare the screen. Sorry about that.
Oh, no worries, no worries.
So what I've done is just I substituted in a larger wavelength version of that over to the right. But there's a problem here if you look subtly, and that is that, the potential didn't go to infinity there. There's no reason to expect a kink in the function. Look, I've generated a kink in the function, and we shouldn't expect a kink unless the potential is going to infinity. That was one of the rules we talked about for the continuity of d psi dx. And therefore, to repair that, intuitively speaking, what I need to do is make the amplitude. Notice I haven't changed the wavelength over here on the right, but I've increased the amplitude. And by increasing the amplitude, I make the slope right there of this part bigger and bigger until it matches. Okay, and that means that as the wavelength is getting bigger, we see the amplitude getting bigger for our case.
Question.
So yes, question, Elvis?
Is that the reason why increasing the amplitude of, say, a flashlight tends to increase its overall energy?
No, the amplitude, yeah, I mean, in that case, the energy, no, this has nothing to do with that.
Oh.
This has nothing to do with the fact that, in fact, in this case, it might be a little bit counterintuitive because, larger wavelengths are lower energy. So it's sort of like saying the amplitude corresponds, to lower energy states here. Yeah, Jake? Right, just based on that worksheet we talked about with the very first worksheet I think we did in chapter 1, we said, look, if you've got a classical particle and it goes up to a higher potential energy, it's moving more slowly. And in that region isn't more likely to be found there, right? Rather than the region with the speeds right through, it's going to spend more time in the slow region. So we need the probability density to be higher, and that means the square of this function has got to be higher. And so that kind of makes sense from that point of view. Okay, so if I were to try to finally amend this, and then what I want you to do is just spend a few minutes working on the other ones in there. I might, try to make this go to an even smaller amplitude there, right? So I would say, let's make it as the wavelength gets smaller, the amplitude should be getting smaller, and then decay to 0 over in the classically forbidden region. So something like that would be a qualitatively correct solution. The reason I want you to do this is not to feel like you're enslaved to these few problems where we can actually do the math, solve the differential equations, and to get an idea of what these solutions look like to the time-independent Schrodinger equation. You've got the tools to do that. So the next one down is supposed to be a large n. I don't really care what n is, but you might make your n like 10 or something like that, or at least look large. And it's almost the same potential, except instead of going up to a finite value, it just goes to infinity forevermore. So it stays at infinity everywhere to the right in there. And the last one is kind of a finite double well potential. That one's a little bit more challenging. The second one's not too much different than the one we did on the board, but the last one, you might have to think a little bit. And I think it's the, what did I say? N equals 4 state? Yeah, for the last one. So spend a couple of minutes just trying your best to draw those, and we can draw them together after that.
Let's take a look. Here we go, Oliver.
I rather enjoyed sketching things. You know, you don't get too many chances to hand draw things in physics, so it's don't be afraid to use your eraser. That's the most important rule. So you want to think about how many zeros you have on there. If it's the n equals 4 state and n equals 1 is ground, you should have 3 zeros. It should only cross the axis 3 times. Right, all the way from minus infinity to infinity, it should only cross. If n equals 1 is ground, then it should cross n minus 1 times. Okay, so some of you are done, some of you are almost done, but let's just kind of go through these together. The second one is really not much of an alteration. The idea is the potential goes to infinity at what looks like x equals 0 and then stays at infinity forevermore, kind of like the infinite square wheel on one side, right? And we want to draw a large n state, you know, maybe n is 8 or 10 or something like that. And the classically allowed region is just the region, you know, where the energy in between where the energy crosses the potential energy. So I've just mapped that out on my psi axes down below. And maybe the first thing I want to do is draw my zeros in, because that's going to help guide my chalk as I go through. So, you know, I'll put, I might say, well, let's put a 0 here. I got to put a lot of zeros in here. And they should get closer and closer and closer together as I head into the right, because the energy is getting farther and farther above the potential energy. I don't know. Just very roughly, kind of like that. I'm trying to make dots that are getting closer together there. And then I've got to have exponential growth or decay. So it's decaying down to 0 as I go off to minus infinity. And then somehow I've got to turn over and hit this first 0. And now the idea is as my wavelength gets smaller, the amplitude should be getting smaller. So, one way to do that is to try to make your amplitude equal to the wavelength. So, there's a lot of zeros there piling up, and then it should go to 0 right at that final location and stay at 0. But there's going to be a kink right there on that last hump that goes down to 0 because the potential goes to infinity. Okay, questions on that? Yeah, I mean, so all of today is just bonus material that's not in Griffiths, but I think it's kind of fun to. No, in the same way that, for the ground state of the infinite potential well, right? We would say that has no zeros. So when it goes to infinity, it may be forced to go to 0, but we're not going to count that. That's a good question. Okay, let's look at the last one, which is a double well. And it corresponds to n equals 4. And if n equals 1 is ground, that means that there should be 3 zeros. So our potential energy looks like this, roughly. It's symmetric with respect to the origin, although I'm not making it look like it is, v of x. And so if I want to draw psi of x, and this is supposed to be n equals 4, right? Our energy is somewhere down here in the bound state region, where n equals 1 is the ground state. I've got to have 3 zeros, and I know my function should be either even or odd with respect to the center, and that means the zeros have got to be symmetrically distributed with respect to the center. And the only way that can happen is if one of the zeros is right smack dab in the middle of the center of symmetry of the double well kind of case. The other one on each side has got to be somewhere in the middle of where the well is. And let's just see how that kind of fits together. So we have classically forbidden over here, classically forbidden in the middle part there. That means it's exponential growth or decay right there. And classically forbidden over here. And somehow I've got to be decaying away as I go to x equals minus infinity, right? So roughly decaying there. Then I've got to start turning over and hit this 0. Once I get over here, I have to start decaying towards 0 again, but I've got to really cross that 0. There's no choice about it. It's hard to think about how this might correspond to. This would actually be a linear combination of exponential growth and decay over there, but actually, since they have the exponential growth and exponential decay have opposite signs, it can actually go through 0. And then somehow I've got to get up so that I'm okay, so exponential growth and decay. So I'm going to head up here and then turn over again and turn over. So I'm ready to start decaying away towards 0 as I go to the right-hand side. So it should have a 0 in the middle, which seems a little bit strange. I don't normally think of this as, and I probably wasn't so careful there, it should actually go over so it's ready to start decaying away to 0 and decaying up there. But we usually don't think of exponential growth and decay looking like this, but depending on the relative signs of the growth and decay, it can look like that. Let's just go back to that. If I share the screen here, let's go back to that Java applet. Here I've made the well separation between the wells really big, so it kind of looks like our worksheet there. So there, I was going to show you how it had to agree here, but I've got to think about this. I guess I'd never looked at this before when I did the qualitative time-independent Schrodinger equation sketching.
Oh dear.
Oh dear, how embarrassing. Huh. Let me just play around with this. Let's decrease, or no. Let's go back to the case we had before where the well separation is smaller. So there we're seeing our symmetry and anti-symmetry with respect to the center, right? We're seeing symmetry and anti-symmetry. Now, what is going on when I increase the well separation? There we've got symmetry and anti-symmetry. I just want to see it. It's all agreeing with what I'm saying here so far, right? We're getting symmetry, you know, odd and even functions, but something is happening as I pull these farther and farther apart. And I'm not sure, maybe it's some sort of numerical glitch in here. There shouldn't be some, you know, phase transition where all of a sudden it stops being even and odd. They're all, see, there is perfectly even and odd. I don't know. I can't see any reason why that simulation should all of a sudden be transitioning to something where the functions aren't even and odd. We have a symmetric well in that example, just like we do here, and the functions are going to alternate even and odd going from the ground state. So there must be some problem when I make this well separation too big in this numerical simulation where something becomes a little bit unstable or something like that. But in any case, I blame it not on me, but on the something in the numerics of this Java applet, which, you know, as far as I can have seen, it's relatively flawless in most other cases, but some sort of weird phase transition in the numerical behavior is happening, right? It's some region right around there where it all of a sudden starts to show states that are not symmetric and anti-symmetric. There we see the nice symmetry. So I'm not sure what's going on there, but pay no attention to the Java applet. I'm the one who's right here. All right.
Is there no like limits of just the separation between the two wells? Interestingly, as long as there's two wells, like they would be asymmetry, despite like how far apart they were.
That's right. We're going to see symmetric and anti-symmetric states alternating regardless. There's going to be less and less, you know, sort of the function is going to go to zero faster and faster in the middle, but there's no limit to it. So there shouldn't be anything special happening at some point on that simulation where I pass a certain well width. And it, you know, if there were, it's certainly news to me, and I don't see the argument for that happening. So that was unfortunate, but, you know, I'll certainly think about that more, but I believe the applet is wrong there. Okay, any more questions on this?
Discussing like a traveling wave, like you saw a traveling wave, you know, like we might not get all the other side, but for a standing wave, like that's what it's.
Well, I think you're thinking of kind of like tunneling, right? Where it hardly gets to the other side. But when we're talking about these definite energy solutions, remember when we talked about tunneling, if I have a, you know, some sort of well that, let's see, what am I thinking of here? Where the potential energy goes down and then stays down forever. And I start with a state that has a relatively low energy here. Maybe all my probability is sort of over here. But if I have a state that it has a definite energy, its probability density shouldn't change at all as time goes on. It's a stationary state. And that means if the state I'm going to draw has a definite energy, then as time goes on, there's never any notion of leakage to the other side. Because as time goes on, the probability density has to stay exactly the same as time goes on. So. All right. Let's put that unfortunate glitch behind us here. And now we're going to talk about what's at the very end of the notes. And this is really to help us, end of chapter 2 notes, to help us with some ideas that come up in chapter 3 that Griffiths hardly spends any time on, but I think they really need to be. We have all the pieces to kind of think about it now, but Griffiths doesn't spend nearly enough time talking about it. It's actually kind of a conceptually complicated notion. And it goes on by the name of Dirac orthonormality, and that's because it has something to do with Dirac delta functions. Okay, so we're going to argue kind of by what we know so far here. So let's go back to the easy case, infinite square well, harmonic oscillator. Those are the cases where the potential makes the time-independent Schrodinger equation have a discrete spectrum, right? Discrete energies, discrete allowed energies. And we said that if it has a discrete spectrum, there's a discrete collection of these psi n's, and we should be able to write any initial state as a linear combination of those psi n's, since the psi n's we're claiming are a complete set. And we haven't seen any cases where they weren't orthonormal yet. Griffiths demonstrates this for both the square well and the harmonic oscillator, that they satisfy this property. And I'm claiming we're going to think about this as an inner product between these two functions. The dot product between psi m and psi n is delta mn. In other words, it's 0 if m and n are different, and it's 1 because they're normalized if m and n are equal. If m and n are just some value, then this is nothing but the total area under the probability density curve, and there it should be 1. Okay, and the question is, okay, so that's some property of these functions that isn't necessarily appearing for us in the case where the spectrum is continuous. So we're going to talk about the continuous spectrum case in just a second, but that's a nice property of those solutions. Another nice property is that this orthonormality can actually allow us to solve for those coefficients up there. If I want to write psi of x0 as a linear combination of the psi n's, here it is sort of expanded out. What we were told we should do is multiply by psi m star on both sides and integrate both sides with respect to x from -infinity to infinity, and then use that orthonormality condition, psi m star of x times psi n integrated from -infinity to mn. We got to think about that a little bit, but this is, we're summing for n, and there's an infinite number of terms of the sum, but this is saying all of those terms are 0 except where n equals m, and therefore the only term that remains is cm there. So all of the terms in that infinite series are 0 except for one of them. And so we found a formula for cm, or equivalently, we found a formula for Cn if we replace the m with the m. Okay. Here's a comment that Griffiths made, and we're going to formalize this in chapter 3. Why do we care about the Cn's? Well, yes, they allow us to write some initial state as a linear combination of those so we can get the time dependence, but they also have a probability interpretation. The magnitude of those Cn squareds is the probability that an energy measurement yields that particular eigenvalue, and the probability of all other non-eigenvalues is 0. So our goal now is to say, well, what if the potential doesn't make the time-independent Schrodinger equation have a discrete spectrum? What if it has a continuous spectrum, like it did for the free particle? Okay, if it has a continuous energy spectrum, like the free particle, and at least partly for the delta function and the finite square well, we had, you know, regions of energies where you could have a continuum of energy values. Then the claim was, you know, for example, for the free particle, we said, well, you know, for the free particle, for any given k value, there's a psi k, and that k can take on a continuum of values. So those time-independent Schrodinger equations, like for the free particle, those would be our e to the I kx kind of functions, right? And the claim is, because we're hoping, there's been no proof of this, and I don't know a proof of this, we're hoping that these are a complete set of functions, we should be able to write any arbitrary initial state as a linear combination of those. And so these g of k's are kind of like our coefficients, the cn's, right? We're saying, put a cn in front of each one of these, it's g for that particular k, and then add them all up. That's a linear combination of them, but how you do it for a continuous case. So we want to ask the same questions about, can we do the same thing with these g of k's that we did before? Okay, so first of all, for these functions, is there some sort of orthonormality condition for these functions psi k, where k is a continuous value? And the answer is yes, even though it's a little bit different than before. It involves a Dirac delta function rather than a Kronecker delta function. The second question, can we use that orthonormality condition to solve for the coefficients g of k? And the answer again is yes. We're going to do it exactly the same way I just demonstrated for solving for the CNs. And we're going to use the new orthonormality condition. The third question is, well, those coefficients in the CN case, when we took the magnitude squared of them, they had a probability interpretation. Is there some probability interpretation of this? And the answer is yes. That's going to be the probability density as a function of k in this case. So what I want to do is that, I mean, it takes a little bit of work to sort of work out how to think about this here. And so, you know, just take a deep breath, because we're going to sort of dive into cases that involve Dirac delta functions pretty quickly. Okay, so let's take those questions one at a time. And this is kind of the hardest of the three. Are these functions an orthonormal collection? So we have a continuous collection of functions, psi k. Maybe k goes from minus infinity to infinity, right? If we have the e to the I kx functions that were the energy eigenfunctions for the free particle, right? And we couldn't really find this normalization coefficient because this is not a normalizable function. When we take the magnitude squared of it, it's just a constant, right? The magnitude squared of this is 1. And so there's no coefficient that can normalize it. The psi k, unfortunately, are not normalizable. And the inner product between two functions, which would involve in talking about orthonormality, seems to be a divergent integral, right? If I take psi k prime and psi k, that's like e to the I kx minus e to the I k prime x. And that integral from minus infinity to infinity, which would be involved in the inner product, doesn't converge. In other words, we're talking about adding together the area under the curve of, you know, this complex function that keeps cycling around. And in the same way as if you integrate the sign from minus infinity to infinity, there's no sense to that. We call that a divergent integral. Similarly, here we're adding up numbers that are cycling from 1 to I to minus 1 to minus I to 1 to I, and it just keeps oscillating around forever and ever. It never converges to anything. So we call that a kind of divergent integral. So they're not orthonormal in the usual sense, and so we're going to use a different word. There is a useful sense in which they're kind of orthonormal if we choose that constant out in front correctly, but we wouldn't say they're just plain orthonormal because those are divergent quantities. Here's always been our goal in the past. We say, you know, those functions, technically, a single particle can't be in this state because it's not normalizable. But it can be very close to that state, and we make it very close by saying, let's put it in that state, but let's put a very wide Gaussian over it, right? If lambda is small, this is perfectly normalizable, but it will sort of oscillate like e to the IKS under a very wide Gaussian envelope. And so those functions should have a perfectly valid inner product. And then after we've taken the inner product, let's see what happens as we let lambda go to 0. That's letting the Gaussian envelope get infinitely wide. And maybe there'll be some sense that we can make of it. Okay? So we've got to take an inner product between two of these functions, one for a k and one for a k prime. That's what we're talking about with calculating this inner product. So let's try that. Here's my guessed psi k. I've bothered to normalize it. That's just, you know, you got to work a little bit to do that with your Gaussian integrals that we've talked about. But if you want it normalized, there it is, perfectly normalizable function. Let's take the inner product between psi k and psi k prime. That's what this means. Okay, I get two factors of this, and I get an e to the I k minus k prime x. And that's of the form of one of the integrals that I gave you, and you I think had to prove it on your homework, something like this, by completing the square. That this kind of function can be written in terms of the Gaussian integral, as long as you're integrating from minus infinity to infinity. We used this on one of the worksheets earlier too. In any case, you have to use some technical integrals, but here's the results. This is the inner product between those two functions. And now we want to see what's happening as lambda goes to 0. That's taking the Gaussian envelope wider and wider. So let's think about what happens. Now, clearly, this has problems as lambda is going to 0, but well, actually, I guess it doesn't. No, all of this is in the exponent there. It looks a little bit funky, but the whole thing is in the exponent of the e there. So as a function of k, I'm thinking of this as a function of k now. It's sharply peaked at the value k equals k prime when lambda gets small, right? When lambda gets small, the coefficient in front of k minus k squared, k minus k prime squared gets large, and that means it goes to 0 really quickly. So it's sharply peaked around there. And if it's sharply peaked around a particular value of k equals k prime, that means it kind of is getting close to a delta function there when lambda is getting small. I'm just trying to accumulate some evidence here. Okay, it looks like a constant times the delta function. And therefore, the question we want to ask is, well, going back to our original function that doesn't have the Gaussian envelope, perhaps if I choose this constant ak just right, then this inner product could be, in that sense, thought to be exactly a delta function and not 2 times a delta function or pi times a delta function, right? We can make it exactly a delta function in the same way before that we had a Kronecker delta function over here. Here we're going to make it a Dirac delta function. Well, if we can do that, if I can choose this ak for each one of these functions in just the right way, so that the inner product between psi k prime and psi k is exactly delta of k minus k prime, we're going to call those functions with those normalization factors in front of them a Dirac orthonormal set. Instead of having a Kronecker delta function over here like we did for the discrete case, we have a Dirac delta function over there. And we'll see why that's useful when we're solving for the coefficients. Okay, so the natural question then is, what should ak be? And we can get the answer from the Fourier-Plancherel theorem, which we talked about back when we were doing the free particle. That tells us if you want to write a function as a linear combination of e to the I kx's, here's how you solve for those coefficients, right? We might have called it phi of k back at that time, but this is how you get between functions of x and functions of k there. So just look for a second. What if I take this f of k over here to be delta of k minus k prime? Then if f of k is delta of k minus k prime, let's see what f of x is. And don't worry about why I'm doing it. We'll see the point in just a second. Let's put in a delta of k minus k prime there. Hey, that's nice. If I have a delta function sitting next to a perfectly valid continuous function, I know how to do that integral. It's my favorite integral to do because I don't have to know anything about calculus. All I do is evaluate this function at k equals k prime. That's how you do integrals with deltas under them. Okay? And therefore, let's go back to this expression where I chose f of k as delta function. Delta of k minus k prime is equal to, well, we just found out that f of x is this. So I'm going to put that f of x under here. When I put that f of x under here, I get this relationship. The details here aren't important, or you can study them to your heart's content in your free time. But if I think of this, this is like telling me that the inner product between two e to the I kx functions is in some sense a delta function, k minus k prime. Okay? So if I write it more formally, I could say delta of k minus k prime is this particular inner product, right? Notice I put one of the 1 over root 2 pi's with one of the functions and one of the 1 over root 2 pi's with the other function. And so it's looking like that constant, in order to make these collection of functions Dirac orthonormal, I want to choose that constant to be 1 over root 2 pi out in front. We wouldn't say it's normalized then, but we would say it's Dirac orthonormalized, those collection of functions. Okay? So the constant we just found is 1 over root 2 pi. And therefore, we can think of this collection of functions that for all different allowed k values, right? At least for the free particle, that would be k equals minus infinity to infinity, any finite k value. This collection of functions is Dirac orthonormal. What that means is, if you take the inner product between any two of them with a different k value, right? A different k and a k prime, take the inner product, you're going to get 0. But if you take the inner product of one with itself, you'll get infinity, but in such a way that the area under that delta function is 1, as areas under the delta function always are. Okay, so we still are not going to say that e to the ikx is normalizable. It's clearly not normalizable. But choosing this coefficient out in front of that function gives us something we call a Dirac orthonormal set, which is to say the inner product between two different functions, even though superficially it looks like a divergent integral, there's another way to see that there's some sense to be made of it, and two different k values give you 0. Okay, so just to summarize what we're doing here, because we're going to push this forward a little bit farther after this. Well, I guess we're still answering question 1. We got to get to question 2 and question 3. So the old thing we said is if we have a discrete spectrum, here's my collection of functions, right? Maybe for the square well, this would start at n equals 1, and I would say, here's an infinite collection of functions. I'm writing it in set notation. We would say it's an orthonormal collection if the inner product, oh, I should have put a star in there. One of these should always have a star and the other one not be starred, right? For an inner product. We talked about that a while ago. The inner product between two of those functions should be 0 if the index is different, and it should be 1 if the index is the same. That's just saying it's normalized, right? So orthogonal and normalized. Now we're saying if we have a continuous collection of these solutions to the time-independent Schrodinger equation, maybe for k between minus infinity and infinity, any real k value, then we'll say it's Dirac orthonormal. And in this case, we'll see how, in this case, because the delta function involves a k and not something like the energy or something, we have to specify what parameter it's Dirac orthonormal with respect to. But Dirac orthonormal with respect to k means when I take the inner product between two of those continuous collection of functions, I get delta of k minus k prime. And well, you might say, well, that's a neat symmetry. We got two different kinds of deltas, but it's going to be very useful to us exactly the same way the Kronecker delta is useful to find those coefficients. Okay. So again, just for the free particle case, which is the easiest collection of these things, the psi k's were e to the ikx, and we said if we take that coefficient out in front to be 1 over root 2 pi, then this infinite collection, maybe I could write it for all real k's, or sometimes people like to let k only be positive values, and then you have to separately put in the e to the ikx or e to the minus ikx. In either case, this collection of functions is the same there. The Dirac orthonormal energy eigenfunctions have a definite normalization out in front, even though before we were saying there's no sense in talking about a normalization because it's not a normalizable function, but there is a sense in which we can put a preferred normalization out in front, okay? And the fact that they're Dirac orthonormal means when I take that inner product, I get exactly a delta function, not 2 times a delta function or something else that kind of looks like a delta function, but exactly a delta function. Okay, so we've answered question 1. Any questions about that kind of idea? So when we write down those energy eigenfunctions, we're going to preferentially put a 1 over root 2 pi out in front of them. At least I'm giving some motivation for that. So there is a sense in which they're orthonormal. It's not normal orthonormality, but it's Dirac orthonormality with respect to that parameter k. Now let's go on to question 2. And one of the usefulness of that Kronecker delta function for the discrete case was it allows us to solve for the CNs. And so the question here is, can we use it to solve for the coefficients? And let me just do this on the board to avoid too much continuous clicking on slides. So let's just do good old-fashioned chalkboard work for a minute. Okay, very quickly to summarize what we had done in the discrete case, right? We said I could write some psi at some particular time as a sum. Let's take like n equals 1 as the ground state here. A linear combination of the psi n's. And the question is, well, how do I, if I know this function, how do I find the appropriate CNs? And what we did was multiply by psi m star as a function of x on both sides. So I'm multiplying by psi m star on that side. Let's multiply by psi m star on this side. And also on both sides, integrate from x equals minus infinity to infinity. And in this case, the integral can move through the sums and it can move through anything that doesn't depend on x. The only things with x dependence are here. So I'm going to integrate from minus infinity to infinity dx, just doing the same thing to both sides. And the magic happens when I realize, oh, wait a minute, this is a Kronecker delta. You can't say this to yourself too many times. It's a very useful thing that happens over and over again, not just in quantum mechanics, but in physics in general. And that's saying, I thought I had an infinite number of terms in this series here, but look, all of them are 0 for the different n's, except for the one special one where n is equal to m, and then this thing is 1. So when n is equal to m, this integral is 1, and I just get Cm. And that's a formula for Cm as a function of for all m's, right? That's how we did it in that case. So let's repeat that argument now using our Dirac orthonormalized collection of functions. So we're saying, here's our Dirac orthonormalized collection of functions, 1 over root 2 pi e to the I k x for k, all k's between minus infinity to infinity. Those are the free particle definite energy states. And the claim is they're a complete set of functions. And so I should be able to write any psi at a particular time as a linear combination of these things with some coefficients that, you know, there's 1 for each k, so I've got to put a coefficient for each k. And I should sum them all up from k equals minus infinity to infinity dk, leaving myself a little room, obviously. And the question is, well, if they're really a complete set, I should be able to do that. How do I solve for what the g of k's are? And the answer is we do the same thing we did before. Before we took one of these corresponding to a different parameter, right, like our psi m, start it over on this side. So I'm going to do the same thing here. I'm going to take one corresponding to a different k, say k prime, take the complex conjugate and multiply both sides by it. So let's put a 1 over root 2 pi e to the minus I k prime x. Let's do the same thing over here. 1 over root 2 pi e to the minus I k prime x. And let's integrate both sides from x equals minus infinity to infinity. That's exactly what we did before. Again, I could put the integral on the outside, but when I look at what stuff depends on x, the integral can pass through anything that doesn't depend on x, and that's just this middle stuff. So we could really move the integral, the x integral, into here. I'm moving the integral into act on just the stuff that depends on x. And I threw in the 1 over root 2 pi's because, hey, I want to keep things organized. Now, the beauty is we just said, we made an argument that this thing should be thought of as delta of k minus k prime. That's what it means to be Dirac orthonormalized with respect to k. And that's beautiful because now this thing is sitting under a k integral, and it makes that k integral really trivial to do, right? If the delta function's sitting next to some other function under an integral, you just evaluate this other function where at the value of k where the spike is, and that it's at k prime. So this is telling me that this whole thing collapses down to g of k prime. So g of k prime is this, and k prime could just as well be k. So I might summarize by saying g of k then has the formula, the integral from x equals minus infinity to infinity of 1 over root 2 pi e to the minus I k prime x times, kx, because I'm changing k prime now to k, times psi of x0 dx. So it works exactly the same way, except instead of the Kronecker delta killing off the sum, the Dirac delta kills off the integral, or makes it easy to do. You don't have to think about how to do the sum. You don't need to know any calculus 2, or whenever you do summation nowadays, infinite sums. I don't need to know any of those things if there's a Kronecker delta under it, because only one term survives, just like only one k value survives here. K equals k prime. All right, questions on that little demonstration there? That's one of the major uses or reasons that you would want to Dirac orthonormalize a collection of functions, even though they technically aren't normalizable, to still choose a preferred value for the, oops, lost control. Forgot I always have to click on this to regain control. So, for example, this is how you're going to solve for the g of k's always. And if we're not talking about the free particle, these won't be those same functions, right? There will be more complicated set of functions for the Dirac delta function well, or the finite square well, or anything like that. We're just doing the easiest case here because we can actually kind of make sense of it. The third question that I wanted to ask again before is, the magnitude of Cn squareds have a probability interpretation according to Griffiths, and we're going to formalize that in chapter 3. What about these coefficients? The magnitude of g of k squared. And the answer is yes, they're going to be our rho of k, rho as a function of wave number. If we wanted, that's wave number is a dynamical variable that we could talk about. It's almost the same thing as momentum, right? B equals h bar k. So we're going to learn that in chapter 3, that the magnitude of g of k squared is rho of k. So it's the probability density under the k curve, it's sort of like our psi star psi is as a function of x. This is the same thing as a function of k. Unfortunately, it's not necessarily a completely direct analogy with this magnitude of Cn squared, because this is interpreted as an energy probability, whereas this one, this rho k, is interpreted as a wave number probability. And the question is, well, then how do I turn it into a wave number probability? And the answer is, well, we can just try to change variables in the expressions that we've already developed from earlier. Okay, so let's try to elaborate on this question. If we Dirac orthonormalize with respect to a different variable, the total energy, in other words, maybe it's worth saying a few more words about this, right? I might have said, for the free particle, we've said, oh, I have this preferred normalization, and my collection of all the Dirac orthonormalizable or orthonormalized wave functions look like this. E to the I kx for k between minus infinity and infinity, any real number value. So that's a collection of solutions to the time-independent Schrodinger equation with their preferred normalizations. Now, we're talking about the free particle. For the free particle, the total energy is just h bar squared k squared over 2m, p squared over 2m. I've written these as if they're parameterized by k, but I could say, hey, isn't k the same thing as root 2m E over h bar if I solve for it there. And therefore, I could write this collection equally well as 1 over root 2 pi times e to the I root 2m e x over h bar. And it is true. All I've done is change variables from k to e here. The problem is that when I do that, if I take these functions at face value, it's not necessarily going to be true that the integral from x equals minus infinity to infinity of psi e as a function of x star times psi e prime of x dx ends up being delta of e minus e prime. And we're, if we're thinking of this as our parameter that we're interested in, denoting these functions by, we're going to find out that this is, in this case, if we choose these functions, it's not equal to that. I would really like it to be equal to that, but I need a different normalization to these functions. This normalization was specific to that parameter k, and it's not necessarily going to work for energy. And there's a lot of work to be done, which I'm not going to go into in class here because I've realized in past years that it's just not sufficiently interesting. So I'm going to refer you to the notes. It's not something that we're ever really going to use directly in class, but if you want to see it, I'm just going to give you the upshot of it. I would really like it, if I'm interested in the parameter e, to have this relationship be true, so that I can, if I say, well, if I want to write an arbitrary psi of x and 0 as an integral over all e's of, an integral over, yes, all e's, some coefficient, I'm not sure what to call it, c as a function of e times psi e of x, right? Integral with respect to e's. I could use that delta function to help me solve for this coefficient. But it's only going to directly help me solve for that if I've written this exactly as, if I've chosen this coefficient that's out in front of this function so that this is true. And that's not necessarily an easy thing to do. Okay, so let me just tell you the upshot of it. Yes, so we need to normalize the psi e's correctly. So let me just tell you what the answer is here. So if I just try to translate and put in root 2me over h bars for each of these k's over there, all I'm doing is changing variables from k to e's, right? So k is root 2me over h bar, k prime is root 2me prime over h bar. This is certainly true, but the question is, can I somehow write this as delta of e minus e prime with some other constants out in front? And in doing that, that's the details that are in the notes. I'm just going to tell you what the upshot is here. And that is that we need to choose different constants that are out in front, okay? We want to choose constants so that, for example, another parameter I might be interested in is the momentum. The momentum is certainly just proportional to k. And I'd really like, if I'm parameterizing my collection of functions of definite momentum, in other words, momentum eigenfunctions, functions that have definite momentum, I would really like to choose the coefficients that are out in front so that this becomes a delta function with respect to momentum. So if we choose a different parameter besides k, and here's some other parameters that are just nice and simply related to k, we have to figure out how to, choose those constants that are out in front to make this exactly a delta function as a function of momentum, or a delta function as a function of energy. And for the momentum case, it's not too bad because P is just proportional to K. So it just gets a factor of 1 over root h bar out in the front. But for energy, because there's a nonlinear relationship between energy and K, you have to think a little bit. And this this normalization constant that's out in front is actually a function of the energy for this function. But once you've done that, it allows you to solve for these coefficients. Maybe that's the last thing we can do today. I know it's a little bit early, but this is kind of dense stuff. And then we'll stop chapter 2, other than the MATLAB stuff that we'll start doing tomorrow. If I wanted to solve this for C of E, and this is an integral from E equals, for all allowed energies, from 0 to infinity, what I would have to do is multiply by psi E prime and integrate. Integrate from x equals minus infinity to infinity psi E prime as a function of x starred psi of x and 0 dx. And what I'm going to get on the right-hand side is an integral with respect to x of psi E times psi E prime. And if that's a delta function, it just kills off the integral in a nice simple way. And that's the usefulness of the Dirac orthonormalized collections of wave functions. You're going to see that Griffiths just casually kind of tosses them in like, one paragraph in chapter 3. And it's a little bit confusing, I think.